First of all, I would like to take this opportunity to thank the Academy for the given opportunity. So today I will be discussing about the work which is going on in my laboratory. Actually, we are trying to develop cobalt based complexes, and then we are using that for the catalytic borylation reactions, which I will be discussing what it is. If you consider the catalytic chemistry, the homogeneous catalysts are playing a key role in many of the chemical synthesis and for the sustainable chemistry. And if you particularly take that, the noble metals which comes from the second and third row of the transition metals of the periodic table actually play a major role in homogeneous catalysis. This can be very easily recognized from the consequent Nobel Prizes in 2001, 2005 and 2010, where the palladium and ruthenium atoms are the major role in that coupling reactions. So what the question now mainly in the synthetic chemistry is that, can we replace this noble metal atom with the base metals? But then why one should be interested in base metal catalytic systems? That's mainly because it is actually very earth abundant, and it also environmentally friendly. Not only that, these base metal atoms can easily undergo multiple oxidation, exist in multiple oxidation states, and then it also can undergo easy 1 or 2 electron reduction process or oxidation process. But by saying that these are the advantages, these can be a disadvantages, because this 1 or 2 electron reduction or reduction processes can lead to the leaching out of the metal atom from the catalytic cycle, which actually stop the catalytic reactions. So how to overcome this problem and make the base metal catalyst system which is efficient as that of the noble metal catalyst? So there comes the role of ligand, which plays a very important role in the development of base metal catalytic systems for the various organic transformations. Here are some of the ligand systems which has been developed for the base metal catalyst. As you can see from here, these are the imidopyridine type or pincer type ligands, what you call as. Here I have given some examples where they used iron as a metal atom, and then this has been used for the olefin polymerization or hydrogenation of alkenes, and which has the efficiency as equivalent that of the noble metal catalyst developed for the same reactions. Not only that, there are also some chiral bidentate phosphine based ligands, and also some kind of beta diketaminotto ligand system has also been developed. And in recently, N-Heterocyclic carbene ligands plays a major role in designing this type of catalytic systems for the various reactions. So in our group, what we are mainly interested in the synthesis of organoborane compounds. Let me just brief what is organoborane. Is nothing but the organic compound which actually has the carbon and boron bond, and this can be a very good source for the carbon nucleophiles. And why it is very important to synthesize organoboranes? It's actually one of the important reagent for the very famous Suzuki-Meira cross coupling reactions, by which you can convert this organoborane into various other functional groups, and it can undergo very nice carbon coupling reactions, and all kinds of functional group you can easily get it from this organoboranes. And how to synthesize this one? You can synthesize from multiple ways by doing the CH activation or CX activation, hydroboration of unsaturated substrates, and so on. And here I have listed some of the diborane reagents which actually can be used to synthesize this organoboranes. And these diborane reagents are once coupled with the carbon, they are actually air stable and easy to handle, and so on. Not only that, these organoboranes are also a very important intermediate for many of the natural product synthesis, and also as an pharmaceutical intermediates. And there are also examples where this boronic esters has been used as a biologically active compounds, and here are some 2 examples currently available as an anti-cancer drug as well as an antifungal drugs. So keeping these two things in mind, we are trying to develop a base metal catalytic systems for the catalytic borylation reactions. And our group is mainly concentrating on cobalt, iron and some of the Lewis acid catalyst. So here I will be focusing on cobalt and Lewis acid based catalytic systems. Let me begin with the synthesis we actually used a NHC as a ligand system for cobalt metal atoms. And if you look at the literature, that it's not it is not like that the cobalt has not been explored for any of the catalytic reactions, particularly for the carbon boron bond formation. There are quite few examples where it has been used for benzylic CH activation, 1,1 diboration, as well as the heteroarene CH activation and so on. But if you look at the catalytic systems which has been used for this purpose are mainly focusing on this immunopyridine type ligands or some kind of phosphine based ligands, and even MOF supported cobalt complexes has also been reported for this organoborane synthesis. So what we have decided that we will synthesize NHC based cobalt complexes and try to explore their activity. So if you take that, it's a very simple synthesis. You just we have to take cobalt chloride and then react with the N-Heterocyclic free carbenes, and you can get this cobalt dichloride, NHC supported cobalt dichloride in almost quantitative yield. And also we were interested in the cobalt 1 complexes. So for that you can just take this already known cobalt PPS3 Cl complex and react with the NHC ligand, like a ligand substitution reaction, and you can get this cobalt 1. But what we found also an alternative method is that you take this cobalt dichloride and you can reduce with the magnesium turnings to get this cobalt 1 chloride. And this compound has been well characterized, and we started exploring that as a catalyst for various reaction and found that that it could be a very effective catalyst for the aryl chloride borylation. As you can see from here, we used this cobalt dichloride and we took this methoxy chlorobenzene, and using base and solvent we could able to get this aryl boronate esters in 97% yield. So why one is interested in aryl chloride borylations? Aryl chlorides, actually chloride reagents are very easily available source than the bromide and iodide. But the thing is, challenging thing is that it is very difficult to activate this carbon chlorine bond when compared to this carbon bromide and carbon iodide bonds. Here I have shown few examples where aryl chloride borylation has been already achieved, but using a palladium catalyst, and there are few examples where copper and iron has been used, but with not many examples, which is actually consist of only 2 examples in this 2 literature. Even some metal free system has been developed for the aryl chloride borylations, but not in an efficient manner. And if you particularly take the cobalt, as we are interested in cobalt complexes, there is also a report for the cobalt catalyzed aryl halide borylation. The main drawback of this system is that it uses the typical ligands which consist of ferrocene, and then also it uses very reactive organometallic reagent which is actually methyl lithium. So our system is very simple. You just take this dichloride, cobalt dichloride complex, and then use a simple base, and in presence of solvent at 50 degrees centigrade you can actually get very good yield of aryl boronate esters. Here are the substrate scope for the aryl chlorides. As see that many of the electron withdrawing and releasing substitutions were well tolerated with our system. And not only that, if you take this like sp2 and sp3 hybridized carbon containing substrate, then we can selectively do this aryl chloride borylations. And also our systems were worked well for the bromides as well as iodide, as you can see, and which includes also some of the heteroarenes borylated products. So now the question is that okay, we have found that the system is very efficient for the aryl chloride and bromide borylations. What is the mechanism behind this borylation reactions? If you see the literature, it says that when cobalt is used as a catalyst, it mainly undergoes an cobalt 1 to 3 catalytic cycles. So we wonder that, okay, maybe our system is also going via this catalytic cycle. So we have carried out some stoichiometric reactions which actually give us some kind of clue. And as you can see from this proton NMR, when you take this cobalt dichloride and the borane reagent and in presence of base, you could see the formation of cobalt 1 chloride, which is actually cobalt IMS2Cl, which corresponds to this proton, and also we could able to see this cobalt IMS2OMe compound. And our boron NMR also was informative, as we could see the immediate formation of methyl OB pin in the boron NMR spectrum. And as I shown in my previous slide, that we could able to synthesize this cobalt 1 chloride in a very efficient manner. Then we decided that, okay, let's use this as a catalyst and see whether the efficiency is still maintaining. Yes, it was actually, we could able to get 92% of yield when using this cobalt IMS2 chloride compound. So based on this observation, we have proposed the reaction mechanism that the cobalt dichloride is getting reduced into cobalt 1, and the transmetallations with the base and the diborane reagents gives this, possibly forms this cobalt boryl, which is cobalt 1 boryl, and which can undergo oxidative addition, gives this cobalt 3 intermediate, and then reductive eliminations gives this aryl B pin and leaves this catalyst back. So after stabilizing that cobalt cobalt dichloride based aryl chloride borylation, we thought of using now cobalt 1 chloride, as we found in the previous reaction. This may be the key intermediate for the catalytic cycle. When we explore different substrates, we found that it can easily do this hydroboration of these vinyl arenes. If you talk about hydroboration, it is actually, everyone knows that it will undergo an anti-Markovnikov addition and leads to this linear boronate compounds. But what we observed in our system is that Markovnikov addition, which actually gives us this branched alkyl boronate compounds. And the important thing in this reaction is that it does not need any base, just a catalyst, and the borane reagent should be enough to carry out this reaction with very good regioselectivity of 95% of this Markovnikov addition product. So I would like to take your attention to the substrate scope, as we could able to get a very good regioselectivity for many of this electron releasing as well as withdrawing substituted vinyl arenes. And also that I highlighted here some of the compounds which actually the generation of tertiary alkyl boronate compounds which are difficult to synthesize in other ways. We could able to efficiently hydroborate when we took this 1,1,2 or 1,1,1 tri-substituted alkyl boronate compounds with a high regioselectivity. I must admit that we do have a drawback in our system. When we use that aliphatic alkenes, we could able to only get this anti-Markovnikov addition as it always goes. So keeping that, and then we went on and analysis the mechanistic study behind this reaction. What we get the information from the proton NMR is that the cobalt 1 chloride does not exist anymore in the reaction while carrying out the reaction. And also boron NMR has given some information of the new compound formation. So we were interested what is that new compound, and as usual we carry on the stoichiometric reactions. When using this cobalt IMS2Cl in presence of HB pin, we could able to isolate this compound, which is actually intramolecular CH activated NHC supported borane, and we were lucky enough to get the crystal structure of that, but unfortunately we found that this is not the catalytically active species. Then we actually move on to the another stoichiometric reactions where we took one equivalent of catalyst and the 2 equivalent of HBP, and then we found that with the help of mass analysis that there is a formation of cobalt 3 species. So with this, what we proposed a catalytic cycle is that when we took this carbene substituted cobalt 1 chloride, first upon reaction with HP pin, it eliminates one of this NHC ligand and makes an adduct with BP pin, so that it makes the coordination site vacant for the alkene insertion. The second step we proposed is this HP pin addition, which actually we found from the HRMS analysis, and then the vinyl arenes added into this cobalt complex and then makes this bibenzylic interaction which we proposed, which undergoes reductive elimination, gives this branched alkyl boronate esters. There is also evidence for this bibenzylic intermediate from the literature, where they have used rhodium as a catalyst for the similar type of vinyl arene hydroboration reactions. Moreover, in our example, what we found that aliphatic alkenes were only giving the anti-Markovnikov addition, which also gives us a clue that it is going via the bibenzylic intermediate, as the bibenzylic intermediate might be is lacking in the case of aliphatic alkenes. So now currently we are changing the NHC ligands and trying to explore the different reactivities. So we have synthesized cyclohexyl substituted NHC compound, and then we did this ligand exchange reaction, and we got this cobalt ICYCl2 cobalt 1 complex, as well as the I-methyl substituted cobalt 1 chloride complex. So when we use this as a catalyst, we could found that this can be an efficient catalyst for the alkyl bromide as well as chloride borylations. And so our optimization says that when we use this ICY as a ligand, sodium ethoxide as a base, we could able to get almost a quantitative yield of this alkyl boronate esters. So here are some of the substrate scope. When you talk about alkyl bromide, we should emphasize on the primary as well as secondary compounds. And also I would like to take the attention to this selectivity of our reaction, where you had this alkene, internal alkene, which does not affect at all during the course of the reaction. We could selectively get this alkyl bromide borylated product, and our system is also efficient for the tertiary tertiary alkyl halide borylations. But the only change what we have done here is that it was not that efficient when we used this diborane, so we changed into a different diborane, which is B catechol substituted one, but then the yield was very good. Our system also works very good for the alkyl chloride substrates, as we have shown here. Even the tertiary alkyl chloride was efficient during the reactions. The mechanistic study, what we thought in this reaction is that I just want to take the attention to this fifth one, where we use this propyl compounds and used toluene as a solvent. We could found these 3 compounds in the GC mass analysis, which actually the alkyl chloride borylation, and the another product is that the toluene borylated compound, and also the homocoupled product, hydrodehalogenated product. This gives us a clue that how the 22% yield of the toluene borylated which we got it might be via the radical formation. So we have done several radical experiments. This is called the radical clock reaction, where you get this, you use this alkenes which cyclized and gives this B-pin compound in 71% yield. And also when we use this kind of substrate, we got this homocoupled product, and the trapping agents like tempo and anthracene, 9,10 dihydroanthracene, gave us the evidence for the radical mechanism. There are similar reports using nickel catalyst for the radical mechanism. So based on that, we have proposed our mechanism for this reaction. When we take this cobalt 1, it forms an cobalt boryl, but then we propose like a radical formation of the alkyl halide and then oxidative addition and gives this alkyl boronate esters. So I think I'll just skip this. So with that, I would like to thank my group as well as the funding agency. Thank you all.